Please be seated. I herewith open the meeting of the Doctorate Committee of the PhD defense of Brendan Caasenbrood and ask him, together with his 2 seconds, to take place behind the lectern. You ready? In that case, I would like to give the first promoter, Professor Henk Nijmeijer, the opportunity to ask the first question.
Dank u wel, meneer de rector. Zoals gebruikelijk wil ik de geachte promovendus vragen om zijn werk in 10 minuten samen te vatten.
Hooggeleerde promotor, graag voldoen ik aan uw verzoek door middel van een korte presentatie. In de afgelopen 70 jaar heeft het veld van de robotica enorme sprongen gemaakt. We zien dat de huidige stand van de robotica in vergelijking tot de eerste industriële robot in 1950 steeds sneller zijn geworden en steeds preciezer zijn geworden. Eveneens zijn we getuigen van een toenemend parallel tussen de robotica en de natuur. Niet alleen in hun ontwerp, maar ook in hun behendigheid. De bewegingen van robots, zoals we geven in de video hierboven, komen steeds dichter in de buurt van de bewegingscapaciteit, zoals we die ook vinden in biologische systemen. Echter, als we gaan kijken naar de constructie van robots, zien we dat deze nog voornamelijk van metaal en kunststoffen zijn gemaakt. Deze materialen zijn vaak zwaar en rigide en verhinderen aspecten zoals veiligheid, behendigheid en duurzaamheid. Al deze factoren leiden ertoe dat bijvoorbeeld industriële robots nog steeds in de kooi worden gezet om botsingen te voorkomen. Robots die vallen kunnen makkelijk breken, wat soms prijzige reparaties met zich meebrengt. En het is lastig om een robot te gebruiken in de medische toepassing vanwege een groot verschil tussen stijfheid tussen de patiënt en de robot. Rond de jaren 60 waren mensen aan het experimenteren met mogelijke oplossingen voor dit probleem. Net als mensen en dieren zou veilige interactie met de omgeving eigenlijk makkelijk moeten zijn. Het idee was om robots te maken van zachte materialen, zoals rubbers, die vervorming konden toestaan, en te besturen met luchtdruk in plaats van elektriciteit. Dit resulteerde in een revolutionaire ontwikkeling in de robotica en de kosten van deze robots was ook beduidend lager. In de bovenstaande video wordt een experiment uit de late jaren 80 gezien. Hierbij is de techniek toegepast om zachte grippen te maken. Wat we observeren is dat deze robot succesvol een glas kan pakken zonder deze te breken en eveneens moeiteloos en snel een schroef kan aandraaien. Het veld van deze type van robots wordt tegenwoordig wel soft robotics genoemd, oftewel zachte robots. En sinds de herintroductie van 2005 is dit onderzoeksgebied alleen maar exponentieel gegroeid. Echter, we zien dat deze technologie nog maar weinig wordt toegepast in de industrie. Een van de mogelijke redenen hiervoor is dat er nog een heleboel open vragen zijn binnen dit onderzoeksgebied. Allereerst, als we gaan kijken naar het designproces van deze robots, blijkt het relatief complex te zijn. Deze systemen hebben het vermogen om op meerdere plekken te deformeren en de deformatie hangt af van de geometrie en de materiaaleigenschappen. Hierdoor zijn bijvoorbeeld beschikbare tools die ons helpen een ontwerp te vinden nog erg beperkt. Een tweede uitdaging betreft het opstellen van wiskundige modellen. Deze modellen kunnen op basis van de input het outputgedrag van de robot voorspellen. Ze spelen bijvoorbeeld een cruciale rol in het verbeteren van een ontwerp. De wijze van modellering is echter divers en de afweging tussen precisie en snelheid bij verschillende modelkeuzes zijn daarom van groot belang. Tot slot gaat het om de besturing van deze zachtrobots, die meestal worden ontworpen met een specifieke taak voor ogen. Bijvoorbeeld het verplaatsen van een object van A naar B. Regelaars bekijken het gedrag van de robot en berekenen vervolgens de benodigde input, zodat de robot de taak correct uitvoert. Hierbij zijn de reeds besproken modellen ook van groot belang. Het hoofddoel van mijn onderzoek is daarom het creëren van nieuwe technieken voor het ontwerp, modelleren en aansturing van softrobots met de ambitie om traditionele robots en uiteindelijk de natuur te evenaren. In mijn onderzoek heb ik me allereerst gericht op numerieke methodes waarmee we een computer een softrobot voor ons laten ontwerpen. Hierbij kijken we eerst naar een doorsnede van de robot. We kunnen dit probleem vervolgens versimpelen door het op te delen in een raster van materiaalblokjes. Paarse blokjes is waar we materiaal plaatsen, blauwe blokjes is waar we de luchtdruk op uitvoeren en grijze blokjes, dat zijn de lege ruimtes. Vanuit zo'n ontwerp kunnen we door middel van numerieke simulatie voorspellen hoe de robot zal deformeren. Deze deformatie koppelen we vervolgens aan een prestatieindex die ons vertelt of de beweging wenselijk is. Je kunt het eigenlijk schematisch voorstellen als een soort van landschap waarbij elk ontwerp correspondeert met een unieke locatie en een unieke prestatie, uitgebeeld in de tinten wit en paars. Echter, we zien van tevoren niet hoe dit landschap eruit ziet. Het idee is dus nu om op een slimme wijze de lokale informatie te gebruiken om iteratief ons ontwerp te verbeteren. Als we dit een aantal keren doen, convergeren we op een ontwerp met het gewenste bewegingsgedrag. Met deze aanpak zijn we dus in staat softrobots te genereren en ook robots die bijvoorbeeld geïnspireerd zijn door de natuur. Wat we hier zien van links naar rechts zijn verschillende stappen van het optimalisatie-algoritme, gebaseerd op systemen bijvoorbeeld die uit kunnen rekken, grijpen of kunnen buigen. Vervolgens zetten we deze numerieke methode om in een 3D-model en produceren we die met een 3D-printer. Hierbij wordt vloeibaar materiaal laag voor laag solide gemaakt door middel van een lichtingsproces. Het resultaat ervan ziet u in de figuur linksonder. En inderdaad, we zien dat het gewenste bewegingsgedrag wordt gerealiseerd. Dit leidt mij tot mijn eerste 2 bijdragen van mijn proefschrift, namelijk het ontwikkelen van algoritmes voor het oplossen van het inverse probleem voor softrobots en het testen en valideren van deze softrobots door middel van 3D-printtechnieken van zacht materiaal. Op dezelfde wijze hebben we ook andere softrobotstructuren ontwikkeld. Na het printen van deze softrobots heb ik me gefocust op het ontwikkelen van generieke modellen. In de literatuur zijn er voornamelijk 2 populaire modelleermethoden. De eerste is gebaseerd op materiaalkunde, waarbij we een zachte structuur opdelen in kleine elementen. Hoewel deze aanpak zeer nauwkeurig is, vereist het echter veel rekenkracht, omdat elk element apart berekend moet worden. Daarom zijn deze modellen vaak in hun berekentijd erg traag. Een andere veelgebruikte methode is de zogenaamde pseudo-rigid body modellen. Hierbij bootsen we de algemene vervorming van de robot na door staafmodellen te gebruiken die op zichzelf niet vervormen. Dit is een gangbare techniek in de klassieke robotica en ondanks dat deze snel is het probleem dat deze methodes vaak niet precies zijn voor softrobots. In mijn proefschrift stel ik daarvoor een hybride benadering voor die elementen van beide modelleringstechnieken combineert. In deze aanpak gebruiken we een eendimensionale curve die de algemene vervorming van de robot in kaart brengt. Daarna gaan we ervan uit dat we deze curve kunnen opdelen in een aantal basisvormen, zogenaamde modes. Deze vormen zijn positieafhankelijk en geven ons dus aan waar vervorming zal optreden langs de beschrijvende curve van de robot. Elke mode koppelen we vervolgens aan een parameter Q die aangeeft in welke mate de mode bijdraagt aan de vervorming. Als we het geheel samenvoegen, kunnen we een numerieke methode opstellen waarmee we het totale vervormingsprofiel kunnen beschrijven. We kunnen vervolgens ook meerdere modes toevoegen om de precisie te verbeteren. Echter, dit is ten koste van de rekentijd. Door te variëren aan deze vrijheidsgraden verandert ook het vervormingsprofiel. Dit stelt ons dus in staat om een brede collectie van vervormingsprofielen te beschrijven met een beperkte set van parameters. Deze modelleeraanpak leidt uiteindelijk tot een wiskundig model waarmee we het dynamisch gedrag van generieke softrobots kunnen beschrijven. We hebben het model vervolgens ook nog verfijnd door elementen toe te voegen die verder de nauwkeurigheid verbeteren van ons model. Bijvoorbeeld het gedrag van materiaal, fluïdische eigenschappen en de dynamica van contactpunten. Met behulp van de modelleermethode beschreven in mijn proefschrift zijn we dus in staat klassieke experimenten van de eind jaren 80 te reconstrueren op basis van de literatuur zo'n 30 jaar geleden. Als vervolg kunnen we deze modellen ook gebruiken om regelaars te ontwikkelen. We doen dit door de output van het systeem te vergelijken met een gewenst outputgedrag. Door deze 2 van elkaar af te trekken, vormen we een signaal, de zogenaamde positioneringsfout, die beschrijft hoe ver de robot afwijkt van een gewenst gedrag. We kunnen vervolgens deze fout gebruiken in combinatie met informatie van ons model om de gewenste regelactie te berekenen, zodat de robot op de juiste manier beweegt. Op basis van de modelleermethode en de regelaar beschreven in mijn proefschrift zijn we dus in geringe mate in staat om verschillende systemen uit de natuur na te bootsen door middel van softrobotica en regeltechniek. In mijn proefschrift heb ik inspiratie getrokken van systemen zoals een olifant, een menselijke hand en de tentakel van een octopus. Naast simulaties hebben we de modellen en regelaars ook getest in een experimentele setting. In de video aan de rechterkant ziet u een zachte robot uitgerust met een flexibele gripper. Het doel van het regelsysteem is om een object te pakken aan de rechterzijde en deze vervolgens te plaatsen in een bakje aan de linkerzijde. In wit zien we het geschatte vervormingsprofiel van de robot op basis van optische en drukmetingen. Zoals u kunt zien is deze schatting vrij nauwkeurig en reageert de robot naar behoren op de besturing. Dit brengt mij tot mijn derde bijdrage, namelijk het ontwikkelen van precieze en snelle dynamische modellen voor softrobots, die toepasbaar zijn op de klassieke regeltechniek. Tot slot heb ik de methodes die verspreid staan in verschillende hoofdstukken van mijn proefschrift gecombineerd tot een software tool. En deze software tool hebben we openbaar beschikbaar gemaakt zodat studenten en wetenschappers hem vrij kunnen gebruiken, maar ook kunnen aanpassen. Het is ontworpen om een breed scala aan problemen te adresseren en is zo geschreven dat zelfs complexe problemen met een enkele regelscode kunnen worden beschreven. Mijn laatste bijdrage is de ontwikkeling van een toegankelijke software die concepten van ontwerp, modellering en aansturing van softrobots, zoals beschreven in mijn proefschrift, samenbrengt. Hooggeleerde promotor, ik hoop hiermee antwoord te hebben gegeven op uw vraag.
Dank u wel. Ik ben zeer tevreden met het antwoord.
Okay, thank you very much. Well, the Eindhoven University of Technology is always very happy when external experts participate in PhD committees. Today we have two of these experts. On the table on the other side, on the right, we have Professor Krijnen from the University of Twente. Welcome. In the middle, we have Professor Ollero from University of Seville in Spain. Welcome, sir. Let me also introduce the other committee members to you. On the left, on the far end table, we have Dr. Pogromsky, who's the co-promoter. On this table on the far end side, we have Dr. Overvelde from Eindhoven University of Technology. On my left, Professor Jaap and Toonder from Mechanical Engineering Department, Eindhoven University of Technology. And my name is Patrick Anderson. I'm Dean of Mechanical Engineering and chairing today's session. The opposition is now continued by Professor Ollero.
Thank you very much. Good afternoon. Joactive from Overvelde. My questions will be in English. So first, I would like to say that this thesis acknowledges the biological system efficiency, which is not just due to the physical design, but rather a sophisticated synergy between design and motor control, which is important, and consider design, consider modeling for control and software development. I like very much the thesis, I have to say so. So I have to congratulate the prompt vendor but also the supervisor for the work. So I have many questions, but I will try to summarize in some very general questions. One of them is related because I mentioned the bio-inspiration. So it is hard to say that everything is bio-inspired in the way in which it's implemented in the nature. As I know that we may have different questions on this topic, I will just concentrate in one. So for example, the McKibben actuator and the below type actuators that achieve linear translation in soft robotics, but it is unclear, or at least I don't know, what made them similar to the hydrostatic muscular system found in nature.
Hooggeleerde opponent, thank you very much for the kind words and the interesting question. So the McKibben actuator dates back quite a while. It's like 1952, and it was initially designed as an alternative to people with polio disease. So they had no function in their muscle. So back then, the guy, I think his name was Joseph McKibben, if I recall, tried to find a safe alternative to develop these type of muscles. So they're driven by pneumatics, and how these systems work is that they have an enclosed volume, and they blow air into that volume, and based on essentially the effect of a balloon, you get a linear contraction. So back in the day, the McKibben actuators were not associated yet with these hydrostatic muscles. Then I think later, maybe in 1960-80, people were doing more experiments of how biological systems essentially moved, and then big inspiration for these systems were, for instance, invertebrates, like think about rainworms or, for instance, the tentacles of an octopus. And they noted that the way that these creatures deform is that they have essentially an enclosed volume of fluid, and at one end of this volume, there's a deformation happening, and fluid is transferred to the other direction, causing a deformation at the other side. So that is how they call, essentially, that classifies hydrostatic muscular systems. So at the time, there was no connection yet between these two systems, and more recently, people are associating the type of behavior that you see, so using fluids for motion, can be associated to systems that we also see in classical nature in that sense. I would say the muscles that we have, they work differently, so we don't transfer fluid from one side to another side, but there's definitely systems that have these type of behaviors that can be closely associated with the McGibbon actuator. I hope that answers your question.
Yes, thank you very much. Just it's a short question, so I also answer short answer in terms of the word repeated in optimization and I will again to have a concrete question. When you talk about optimization benchmark, what is the objective when finding the optimal topology of soft fluidic muscle? So there is a criterion to compare the different topologies, and why you say that this is the optimal?
It's a really good question. I think the answer for a global optimum is no. So I think there is I think it's also, I cannot say this for sure, but I think for topology optimization, at least the techniques that we use described in my thesis, it can be very easily proven that there is no global optimum for these type of structures. So think, for instance, about a classic beam where you do a particular tension on one side and you say like, okay, I want to optimize the compliance of my system. So what they have shown, I think already in the 80s, based on the work of, I think, Sigmund, he's a big name in topology optimization, is that there is no optimal solution for these type of systems. And the general idea is that for topology optimization in general, there exists nothing like a global optimum. So I think what I mean in my thesis for an optimal solution is optimal in the sense compared to classical engineering approaches. So in my dissertation, I shown, for instance, that there are other solutions that exist that perform, let's say, the linear extension. And then you get, using this topology optimization, this bellow-like structure. So these bellows we have already seen in classical engineering. We've known from them like many, many years. But what's interesting to see is that the solutions that we get is essentially this concave form. So you get more extension range than, for instance, the classic bellows, which have a flat top. They don't use this concave structure. So you could say to some extent the performance of these type of systems is better, but I can almost guarantee that there's other design solutions that will outperform this type of convex shape. So to give a short summary on your question, I think optimal is a very loose term that I use in my thesis. Yeah.
Okay, thank you very much. I think that we have out of time, but just a comment that to improve the publications later, it could be good in some cases to have comparisons, for example, the energy consumption and the efficiency in chapter 6 with other controllers and publish this comparison, because I'm sure that you will get good results, so you can publish these results. But this is not a question.
Okay.
Now I'll transfer the question in a recommendation.
Okay. Thank you very
That's
much.
all. Thank you.
You already satisfied, sir?
Yes.
Okay, thank you very much. Then we continue the opposition with Professor Krijnen.
Geachte promovendus, congratulations with your thesis. It's a beautiful piece of work, written down very well. Of course, it allows the soft robotics community with new tools, which I think is very useful for many people. So thanks a lot for that. I've read your thesis with a lot of interest. That also resulted in many questions, and I don't think we can have them all, but just let's give it a try. First off, a question about the soft robotics and biomimetics. In your societal summary, you describe how soft robotics can help mankind. E.g., you write, another advantage of soft robotics is their ability to operate in unstructured and unpredictable environments, such as disaster zones or outer space. And also in abstract, you mention how soft robotics can be inspired by nature, e.g. by the tentacles of octopuses or the trunk of elephants. I've always been very fond of biomimetics and bioinspiration. Still, if you look at the tentacles of the octopuses and the trunk of elephants, they are heavily depending on large numbers of actuators. So for the elephant trunk, that's about 17 or so, and it actually means if you want to recreate that more or less, you also have to have these number of actuators. And this suggests a question, how do you think we can incorporate these large number of actuators in soft robots? And so ideally, it should not be based on pneumatic actuation, I guess.
Hooggeleerde op het moment. Thanks for the nice words and the interesting question. It's a good question in the sense that I think pneumatics at the moment is the easiest way of incorporating essentially something that is very similar to our muscular system. Of course, it becomes more difficult the more of these muscles you want to embed in your soft actuator. So I know 3D printing techniques, for instance, are getting better and better with producing these fluidic channels and also incorporating essentially pressure chambers inside soft robotics. But indeed, I do think that at some point we will hit the limit of what we can, for instance, fabricate with a laser, and therefore we're limited in the fact how many muscles we can incorporate in these robotic systems. I think the question, though, is why we would like to incorporate as many muscles as we can in these robotic systems. Because I think that the difference between a robot is that it's typically designed with a specific task in mind. So that, in my opinion, would draw some kind of difference between what we want from a robot and what we want from a biological system.
Okay, but that's an interesting point, because you take biomimetics, you want to have something which nature actually delivers more or less.
Yes.
But you're also telling me, and I agree on that this what nature does is actually highly optimized for the ecology of that organism. So why should that be relevant for what we want to do? I mean, the application of the things that we do are completely different. So why should a biomimetic solution be a good solution for our technical question?
It's a good question. I don't think I have an answer to it that is very sound at the moment, I would say. I think when we look at rigid robotics at the moment, there are particular applications where we say these type of systems lack something. The classic example, for instance, is in medical care, where using rigid robots to do particular operations, and they're very tightly controlled. And typically the compliance of these systems comes not from a mechanical perspective, but from the way that they are controlled. So I would say at the moment we're not using soft robotics yet in an advanced sense where rigid robotics is. And I think that gap can be filled by looking, for instance, at biological systems, where there is, for instance, a closer interaction with the environment. Is biology the best inspiration to look at in comparison to our engineering principles? I don't know yet, but I think it's something that we should definitely investigate, because we do notice that there are some lacks with the current way that we design these type of systems, and a possible answer can be that this solution might be found in nature and the way that nature solves these type of
So in summary, you could say that bio-inspiration is maybe more applicable than biomimetics.
Could you elaborate on the difference between bio-inspiration?
Well, biomimetics is basically mimicking what you see in nature, whereas bio-inspiration would be the act of getting inspired by something you see in nature and then using that in a different context.
Yeah.
Or the same, but at least only taking the inspiration.
I think in general, bio-inspiration is probably the best approach to go for then. That you take, that you let yourself inspire by sub-solutions that together help you with developing better robots. Yeah.
Okay.
Because at the moment, I'm not aware of any biological system that does operation except for us humans. But that could be an inspiration as well, of course.
Yeah. I want to move my question to a different subject, which is on sensing. You know that in my research, I spend a lot of time on trying to incorporate embedded sensing in 3D printed materials. And also in your thesis, you mentioned sensing a number of times, especially when regarding biomimetic examples, of course, where you elaborate on all the sensing that is in the organs of the different animals. Yet in your control experiment, you use an IMU and you use a camera. IMU, you could still say it's still attached to the soft robot, right? So could be embedded as well. Mm-hmm. But at least the camera is not something that you want to carry with you, right?
No.
So what are your ideas about sensing in soft robotics, and then both, let's say, in proprioceptive as well as in environmental or interaction sensing?
So In the ideal case, you would like to have these sensors embedded into your robot. In my thesis, we've done indeed IMU sensing. We also used essentially optical trackers to track the tip of the robot. But what we also use are the pressure signals. So I think in chapter 5 of my thesis, I combine essentially the information from the tip of the robot with pressure measurements. And based on that, we can get relatively good estimate for the deformation of the systems. The only problem, of course, is that these type of sensors, pressure measurements, are relatively slow. So if you have slow movement in your robotic system or in your soft robot, you can get a quite a good accurate measurement of a prediction. But if you're doing faster motions, I would say we need something different, and that's why I attached the IMU. So then you include essentially a sensor that can measure at 200 hertz or something.
Now let's look ahead a little bit. Let's look into the future where we maybe have much better control of 3D printed sensors and so on, so we can embed them and do things at will. What would be your strategy if you could use those sensors with respect to what sort of sensors would you like to use? From what sort of materials do you want to make them? Where would you put them in the robots? Maybe first these three, and then I have another follow-up.
So I have to. So where you put them, what type of sensors, and there was something else though?
Materials.
The materials. Okay. I think where you would put them, preferably at the task, I would say, because in general, like if you, for instance, look at our hands, we have the most sensors in our hands and our lips, essentially the things that we operate with. So my advice for placement would be look at the task and try to find essentially a strategy where you place the sensors based on how well you can reconstruct the robot's ability to perform that task. Then material-wise...
But could it be more precise? Do you have more indications where you should put that?
So for instance, the point is a bit that you don't have to put the sensors at the location. For instance, if we want to do some classic trajectory tracking of the tip of a robot, then you could say, okay, you can place a sensor in the tip of the robot that measures the distance between the task and the robot, of the object and robot itself. But there could be other locations on the body of the robot itself that are well enough able to reconstruct that information at the tip. So I think sensor placement is in general a tricky subject if you don't have a general description of what you want the robot to do. So in my thesis, I did a bit of research as well on sensor placement, and what we did is that we essentially have this curve, and we decompose this curve in a set of these basis modes, so these shape modes. And what I discovered is that if you can measure, for instance, at the points where these curves cross the zero section, and you do that for multiple locations, you can essentially separate these type of curves and then get a better description of the overall deformation of your robot. Mm. Now, if we're interested in only the end effector of the robot, then I would say this technique of placing the sensors at these cross sections is not a good approach because you're interested in something at the tip.
Well, I'm not sure. If I move my arm, I know exactly where it is, more or less, right? Even if I don't see it. And that's from my...
Exactly is a general, is a difficult term, I guess. Yeah. I think you have a good estimation of where your hand is within a particular region of uncertainty. And when talking about these systems, at least I believe, they're not rigid robots. So for rigid robots, we want them to be fast, we want them to be precise. But for soft robots, I think we can allow for some degree of uncertainty for these robots still to perform tasks relatively well. Yeah.
Maybe bordering a little bit already on what you have said before, but what would be the strategy? If let's say you want to have a sort of algorithmic way of positioning your sensors, would there be an easy design rule or an easy algorithm, or like everywhere where strain is maximum or minimum, or where, I don't know.
I think it's better to have too many sensors. So this idea of redundancy, perhaps. So, but if you're looking into cost constraints or constraints of how many sensors you can place, then those are your hard boundaries, I guess. Like you say, okay, I can only afford 3 IMUs. Then the question is very easy. Okay, I'm gonna optimize these type of IMUs. But if you say, okay, I can add as many sensors as I want to, I have the ability to do it using 3D printing, then I think generally an ad hoc strategy would work well in the beginning. And then maybe later you can use, for instance, optimization to refine particular type of, Like I'm familiar with some work where people have a particular soft robot and they have these liquid metals. They're basically just wires of liquid metal throughout the body of the robot. And what they do is that they initially have a lot of arbitrary lines of these sensors through the robot, and then they try to slowly optimize to check, okay, which of these sensors we can eliminate from our system. And the nice thing about that type of strategy is that if you have a different distribution of these type of lines in the beginning of your system, you will also end up with a different configuration at the end, even though you use the same type of optimization. So there's also this non-uniqueness of solutions.
Yeah, so you could go along also these sort of genetic algorithms and then maybe also modeling.
I haven't tested it myself, but I believe that could be a good approach to start with.
Yeah. Director, do I have some more time or should I?
Well, if you have a short question with a short answer, that's allowed.
Yeah, maybe one really short question. And your Sortoki toolkit has been made for MATLAB. Why not in Python?
So it's an interesting story. I try to tell it very quickly. I started in MATLAB, then C++, then back to MATLAB, then Julia, and now at the moment I'm thinking, okay, I should have done something completely different in the beginning. So I think MATLAB is good because it's a very easy language. It tells you there is an error in your code specifically there. C++ is a bit more tricky. Julia, I tried Julia as well. There's a version of Sortoki also written in Julia, very rudimentary. If I could make the switch, I would write it in Python, because there's a big community of...
Specifically, I think because there's, of course, a big maker community that would benefit from that.
Yes.
I think MATLAB is very academic in the end, right? And not many private persons have a license. So.
It's true, yeah. But then academics, they're also slowly merging to Python. For instance, in the AI community, Python is very well used.
Director, I'm satisfied.
Okay, thank you very much. Then we continue the opposition with Dr. Overvelde.
Geachte promovendus, I read your thesis really with great pleasure, and I actually really appreciate the chapter 6 on the Sortoki and trying to translate these efforts also to more broadly to a broader community. Before getting to some questions maybe related to that, I wanted to start with a question related to proposition 2. So I wanted to ask one of the paranymphs actually to read proposition 2.
Proposition 2 reads the following. Regarding both the topology and the material as onum properties in the design optimization for soft robotics is essential in discovering new mechanical configurations, which may not be found when either is already assumed or assumed to be known.
So maybe my question is not about the proposition, but I want to brainstorm a little bit about this, because your thesis is also in large part about control. And I actually was wondering how much does the controller, an assuming specific controller, will affect actually the optimal topology. So if you would assume a highly complex controller, let's say you have a robotic arm, you have a computer at your disposal, and you have to design the best actuator, how would that actuator look in comparison to when you have almost no possibility for employing a controller?
Zeer geleerde opponent. Thanks for the nice words and interesting question. It's a tricky one. So in my thesis, I assumed essentially that the controller is always on. So if I essentially repeat my optimization, I get roughly the same result. So even if I make it in a different initial condition, the solutions will always converge to something that is very similar, which actually I find quite interesting. So that means that there are these type of solutions that are basically independent of material, and they kind of give you a general solution for, okay, this type of geometry you should have for these type of motions. I think if you include control, then the question is going to, the solutions are going to be a bit more difficult to find. I think the best step to start is, instead of having, for instance, a constant input, having something that is periodic. To, like, let's say you want to have a robot that can move forward as fast as possible or something like that. Then you could include, for instance, controllers that try to make sure that this oscillation is, for instance, kept. So based on the deformation of your robot, you could backfeed that into some kind of controller that ensures that these oscillations are well maintained. So how to solve this, I have no idea. I think it's probably some kind of parallel optimization where you both update your topology and maybe the phase and amplitude of these controllers. Just include all these variables into one big mega optimization, I guess.
That's always a bad idea.
Yeah, just more parameters is better. But again, like the issue is, of course, then if you do everything all at once, you also lose oversight of what you're doing, I guess. So my feeling would still be that it's like, I'm a control engineer, so we get a system in our hands and then we design a controller afterwards. But I know for sure it's possible to include these all together.
So I guess then it might, you might have to change your objective function in your topology optimization in order to achieve that, or something like that.
I think something that you have to include is, for instance, control effort.
Yeah. I was hoping you would say that your Solitoki kit could actually do that for me. Could I use
maybe
that?
In a month or something. I don't know. Maybe not yet at the moment.
Because it has all the functionalities, right? But
no. So what we need then is an analytic expression for the controller part in your objective function, which I don't have at the moment. But we could include it very easily if I have a bit of time, I would say.
But that, I guess your
easily
time
is maybe a strong word. I think so.
All right, thank you. I have a next question, which is related to some of the modes you assume in your in solving your, or in your model. And there's actually a question related also to figure 6.6 in your thesis, where, of course, I picked this figure because I've worked on it quite a bit. It's about the metamaterial, so you probably know it.
Mm-hmm.
And so here you actually show that when you apply a initial deformation, you change effectively the modes that appear first, right? So if you would, for instance, do a vibrational analysis on an undeformed and deformed structure, probably you have a different modal basis. Mm-hmm. Now in your thesis, and that's, I guess, in a different chapter, I think chapter 4, you use K as a number of modes. It's different modes, I understand that, but I was wondering, how would that basis need to change if you have large deformations or if you have interactions with the environment?
Yeah, so I think a nice example is maybe later in the chapter, where we use essentially this technique of bases based on this Brunet actuator. So what we see here in the top figure are essentially the modes of deformation corresponding to this type of system. So it's not included in the thesis, but what I did is that I essentially did a simulation of periodic input, and then I changed the amplitude a bit, changed the frequency a bit. And what we noticed is that these modes, they will come differently based on each example set, or I say that the parameter set, or you say that data set, that's the word. But the changes are quite minimal in that sense. So I think it really depends on the geometry that you choose for your systems. I think that the example that we showed earlier with these type of buckling modes, mm-hmm. There's a very sharp transition in geometry. And I think that will make it difficult to essentially find a set that is suitable for every mode of operation, I guess. You could say that you could maybe include the whole thing, that you also include the modes from the beginning and the modes from the end, and just make your set very large, but then of course you struggle with computation time.
Yeah. I see your point. So you're saying that your model, the basis is quite general in that.
Yeah.
In that sense. So you would go for maybe for complex things, maybe a larger modal basis, or would you, and not for maybe a changing modal basis, or am I saying something very
no? So
stupid
it's a good question. So I haven't done studies on this myself, but I know there's something, for instance, parameter varying systems where you essentially enhance your system. We say, okay, we have a selection of modes that we are not interested in and that we are interested in, and we switch between them very slowly or something like that, depending on the mode of operation that we're in. Yeah, but again, I haven't done this myself, so I'm not an expert. But I do notice that if you choose your geometry well and you know the range of operation of your system, you can find a particular select set of modes that are sufficient for describing your system. Yeah.
Maybe as a last question, okay. Related to this, because you know I like nonlinearities. So what now if your actuator is highly nonlinear, or maybe it buckles? I know you write in your thesis you don't like ballooning and you don't like nonlinearities, but what if, right? What would you have to change to your basis, to your model basis? Do you have to change it?
Yes, for sure. Yeah, like I think indeed then we come back to the original point that you just have to include a lot of these modes. So that the issue with this type of analogy is that you assume that you can essentially decompose your system into these set of modes. If this is still applicable to systems that have very sharp nonlinearities, I'm not sure if that still holds in that sense. So I would say the techniques that I describe in my thesis are not yet applicable, not ready yet for these type of systems. Yeah.
All right, thank you.
Okay, thank you very much. I'm going to take the opportunity to ask a question myself, geachte promovendus. Could you show Appendix E? It's on the Newman beta solver.
Do you know the page number?
No, because it doesn't have a page number.
Oh, shit.
It's somewhere in the end.
Yes.
I guess it will be around 2:30 or so. Yeah, I've just a quick question. I looked at the solver and I have an idea what you're doing. In E4, you mentioned that this alpha plus is a parameter between 0 and 1. How do you choose it?
Dear Chairman, thanks for the question. Ad hoc, I would say.
No,
I think in general, at the moment here, I assume this parameter to be fixed, but I would say that the latest version of my software chooses this parameter adaptively. So we have here a classic implicit function, which we have to solve. And then we can use very standard techniques to find this optimal parameter alpha to converge very quickly.
I think there's quite some theory how to choose it. And the final question, in E4, you need to take the inverse of this A as a function of Wn. Is this Hessian? Isn't that very expensive?
Yes. Yeah. So I would say like the models that I use in my thesis, the B models I can do real time. The FEM models are horrendously slow. And also because I'm using MATLAB.
Yeah. Also here, I think there are ways to improve this.
Yeah, so the ways that there is, for instance, the secant method, or what we do is that we just say, okay, it will not change that much. We'll just use it for a few iterations. But at some point, you run into stability issues. Yeah.
Okay, thank you very much. And we continue with the secretary, Professor Toonder.
Dank u wel, meneer de rector. Geachte promovendus, congratulations with a very nice piece of work. It's very interesting. And I especially like many things. I like chapter 6, you know, the fact that actually all your developments come together in this toolkit that is now available to the community. So that is really giving impact to the field. That's very nice. I also liked, and that's maybe my first very small question, is your historical overview that you gave of soft robotics. It's always nice to see that. I mean, for some people, unexpectedly, you see that soft robotics was already done when it wasn't even known as soft robotics, right? In the 60s. My very first small question is actually, you mentioned somewhere in the introduction, I don't know exactly where, that the term soft robotics was sort of coined in 2008. Do you know who actually coined the term? Because I don't think that is exactly, because there is a citation, but that's a paper of 2018, so that cannot be the. So do you know who?
Hooggeleerde open-end. Thanks for the nice words and question. I have no idea. No. So I know, like in the 80s, people were coining the term, for instance, flexible robots, hyper-redundant robots. But nowadays, if we talk about hyper-redundant robots, they're not necessarily soft. It's actually interesting because we have a discussion now and a review based on that term exactly.
Okay.
I think at some point there was just a growing community and people saw it as something opposite to rigid.
Right.
And I think it's maybe a term that was
so it cannot
developed.
be pinpointed to one specific publication.
I think there's definitely a few researchers, for instance, George Whiteside, that was very big and then kind of introduced like, okay, we're from chemistry, but we're doing robotics now.
Right.
And if you see those big names, then at some point they coin terms and then it catches on.
Right.
So personally, I think it's indeed a nice name for these type of robotics. Maybe not necessarily accurate for all type of systems because of like when do you call something a soft robot? I would say. Yeah. But no, I don't know who coined this.
Well, you give a definition, right, yourself of soft robotics.
Yeah,
maybe we get back to that later. Maybe first also a little bit about chapter 6 about Soratoki, the toolbox. I like that very much. First question is, how is your toolbox different from other toolboxes? Because you mentioned some of them on, I don't know, somewhere page 34, right? So apparently there are some existing, let's say, models or toolboxes or software, or how you call them, Sofa, Divtachi, SimSoft, and others. So how is your toolbox, let's say, standing out?
The other way. While I answer this question, I can probably also talk.
It doesn't. You don't need to show it because it's just a general question.
Okay, so in general, Soratoki tries to cover a lot of aspects of soft robotics.
Yeah.
So when I started my PhD, the difficulties that I was facing was that there was simply too much. So I started initially with these type of FEM models, and then slowly added hyperelasticity. And at some point, I came to the conclusion it's almost impossible to use these in control. So then I switched to a modeling technique for these type of beams. So I would say during my PhD, slowly, there were also other toolboxes that did very similar things to what I did. I would say that the models that we use, for instance, for these beams are very closely related to the SolarSim, which is also recently, I think, published. I think where Soratoki then in general comes in as differently is that we try to be a jack of all trades.
Right.
I wouldn't say that the techniques that I developed for these beam models are way better and faster than, for instance, the ones from SolarSim, but they allow things that SolarSim can, for instance, not do. So you can start with a FEM model, you can simulate that statically or dynamically, and you can use this, for instance, as a virtual simulator and then extract models that you can use for control. This is something that you cannot do with SolarSim, for instance. Yeah. On the other hand, you can do topology optimization, and we also made a physical system that you can control a robot in real time. You can connect it with MATLAB. So again, it's tries to cover a broad aspect of the multiple disciplines in the field.
Yeah. Okay. Thanks. So. I think there probably are also limitations, right? And it may actually be something that is maybe in general present in the soft robotic fields and maybe also in the thesis, that it's all about, let's say, fluidically actuated systems. So the question was already a little bit, was already a little bit touched upon before. because as you also mentioned in your thesis, there are maybe other systems that you could call soft robotics that are actuated differently. So you could think about light, you can think about magnetic actuations. We're doing ourselves magnetic elastomers, for example, and try to make soft robots from this. So basically my question is, let's say, methodology that you developed and the models that you developed, are they very specific to the fluidic actuation, or can they also be turned around, or maybe some of the concepts can also be used to look at different material systems that you could also classify as soft robotics?
In chapter 5 of my thesis, I wrote a general modeling strategy for fluidics, but also tendons. So there are some researchers that use tendons to manipulate these type of robots, like puppets. And indeed, like there's many different types of actuations, like in light-based actuation, which is thermal, if I believe. So indeed, like you use light, but
you
it
can
converts.
actually have molecular changes.
Okay.
Induced
Then
by
I'm
light.
wrong in that sense.
No, it can also be a thermal either.
Okay.
Actually,
I think from a FEM perspective, we could theoretically use the same type of models that I also described in my thesis. I think in general for these beam type models, we could do it, but it's more difficult to describe exactly where the forces apply to this soft structure. So in my thesis, I tried to describe a bit the distinction between soft body and soft actuation. So where the body is essentially the conduit of the actuation and the sensing talks through the body and then to the actuation. So I think the tricky part is in then describing how to formalize this actuation part in the sense that we can describe it in these type of beam type models. I do think it's possible, but it's definitely more tricky than fluidics. Because fluidics, you already design something with a particular geometry, which deforms in a particular way that you expect it. With materials, I'm not sure how that works.
Because maybe at some point we need to do this, because, can I follow up? Because I want to go to actually proposition number 6. So maybe, so then you also have some work to do now to read proposition number 6, please.
Proposition number 6 is actually instrumental in the development of soft robotics. Dominance may limit the progress in areas such as bandwidth.
Yeah, so that means actually if we want to overcome these, right, if your, let's say, proposition is indeed correct, then we need to move on. So can you say a little bit more about these limits? So why is the fluidic actuation limited in this sense?
So in general, fluidics involves that you have to transfer fluid from A to B. And in that process, there's always a delay. So if you compare that, for instance, to electrical actuation, it's almost instantaneous. And then if you want to think about, for instance, I want to make a soft robot that's very fast, you're at some point limited by the physics of these systems. The same as, for instance, if you want to make robots that are as big as an elephant, you have to involve very big fluidic vessels, and you have to pump a lot of fluids to these systems. Alternative methods of actuation are indeed, like you could use materials. But in general, I think that the proposition is not meant as an attack towards fluidics. So there are things with fluidics that you can do very easily, for instance, making logic with fluidics. What I tried to say with the proposition is that there are particular limitations towards using fluidic actuation. But what I see in the field is that if people do soft robotics, they instantly go towards fluidics, which is not necessarily the case in mine. But you shouldn't instantly, they're not associated together.
Okay. Because you also mentioned autonomy, right? So this is because, of course, you have to connect tubings to this. I mean, the fluids need to be transported from some actuating mechanism towards the robot
so
itself.
there are techniques where you have, for instance, a little pressure tank that you can connect to your robot, and then you can have it fully autonomous. But at some moment the pressure tank runs out. But it's the same as a battery, I would say. I think that the thing that we're struggling with the most now is making it have a very large energy capacity with fluidics. It's tricky to do. Like with batteries, we have them for quite some time already. So we have figured out how to inject essentially a lot of energy into the system and compactly store them. With fluidics, it's maybe something that is slowly coming up.
Right. I guess my time's up.
I'm pretty sure your time is up.
Okay. So thank you very much.
Then we go finally to the co-promoter, Dr. Pogromsky.
Thank you, Mr. Chairman. Geachte promovendus, dear Brendan, I have a couple of questions to you, and I start with a question on chapter 5. So in that chapter, you took the following approach. You expanded the strain in the form of infinite series, which then you truncated into a finite form, depending on the number of base functions you take into consideration. And for it, basically it means that you get infinite number of models. And each model is a mechanical system. It means that it is equipped with the energy. And we can use energy shaping or passivity-based control in order to control it. So since the energy is quite important, my question is, what can you say about the behavior of the energy if the number of base function increases?
Zeer geleerde co-promoter, thanks for your question. So what we do notice is that if we increase the number of modes, we get some kind of convergent behavior when we look at, for instance, the outputs that we get from our model. So if we compute the inertia matrix or the Coriolis matrix, we get closer and closer to this same number for increasing number of modes. So my feeling would be that if you include a lot of modes, at some point there is minimal changes into the energy of your system. Is it so that if you include fewer modes that you get lesser energy, or if you include more modes that you get something that in general is more energy efficient? I cannot give an answer to because I do not know how these parts of our model converge with increasing number of mode shapes, I would say.
Okay, and that motivates my second question. So in a traditional, conventional, rigid robotics approach, we do something opposite. So we start with the energy function, and then by means of routine technique, we derive Ollero-Lagrange models. And in your thesis, you propose something upside down, to start with the model and then to end up with the energy. So what came first, the hen or the egg?
That's also.
Can you comment on that?
Yeah, what came first? I think we had many discussions on this. Indeed, like the chicken-egg problem. So the moment you include a controller, it's very tricky. I have to think about this. I think in general, it makes sense to think about what do we want our robot to do with a task in mind, and then essentially limit the type of controllers that we would apply to our system. So I think the problem is now that we have our system, we model it, then we include our controller, and then we apply it to the physical system. So I think the problem with that is that this controller and the model might, for instance, be different. They have, for instance, different energy levels. So a different approach that I would say, or maybe would suggest, is to try to do these things together. That you say, okay, I have a particular formulation of the model, and then from there, we essentially truncate it. I hope that answers your question.
Yeah, to some extent.
Yeah, so to comment, though, on this, the types of truncation, I would like to refer to this figure. So what we do here is that we essentially have a system of very high order, but we apply a controller of a lower order. So in this case here, for the first set of robots, we essentially apply this BCC model. And what we do see is that even though you have a very poor approximation of your system, your robot can approximate this REPL.
Well, we have just learned from the beetle that the hour has passed, which means that this part comes to end. So I would like to ask the candidate together with his 2 seconds to take your place back into the audience. The committee will now withdraw for deliberation. I adjourn this meeting. Please be seated. I reopen the meeting and ask the doctorate candidate, together with his 2 seconds, to take place in front of this table. The doctorate board of Eindhoven University of Technology, represented by us, has examined your dissertation and heard your defense of it. On the grounds of the aforementioned, the doctorate board has decided to award you the degree of doctor. I request that the first promoter acquit himself of the duties entrusted to him.
Uit kracht van de bevoegdheid ons toegekend door de wet en namens het College voor Promoties bevorder ik u, Brandon Jonathan Caasenbrood, tot dokter en verleen ik u de rechten die verbonden zijn aan de dokterstitel. Deze toekenning geschiet met het predicaat cum laude. Ten bewijs hiervan overhandig ik u het diploma, ondertekend door de rector magnificus en de promotoren.
Please be seated.
Dr. Caasenbrood. Dat is toch wel bijzonder, Brandon. Ja. En dat is diverse keren werd je al wat misplaatst. Als we weer een artikel wilden publiceren, werd je misplaatst als dokter aangeschreven. Ik heb je daar vaak op gewezen dat dat helemaal niet klopte en dat je op zijn minst toch daar nog wel even werk aan moest doen. Bovendien, cum laude, het is echt een fantastisch resultaat. Ik wil in mijn woorden toch even terugblikken op jouw historie binnen de groep. Ik wist het niet precies meer en daar, Sascha heeft mij daarbij geholpen. Het was 2017 dat je afgestudeerd bent met LOF. Nou, jouw boekje en jouw cv daarin, ja, dat zegt wel dat je afgestudeerd bent met LOF, maar niet waarop, bij wie of wat dan ook. En ik had zoiets van, is die man al zo lang eigenlijk in mijn omgeving geweest? Ik twijfelde daar zeer aan, maar gelukkig, dokter Pogromsky hielp mij, ja, en hij stuurde ook mij het afstudeerverslag. Nou, mocht u daar nu in geïnteresseerd zijn, en jij zelf voorop, ja, de titel is ongeveer hetzelfde als je proefschrift. Dus of we hebben 5 jaar lang gewerkt aan wat je al gedaan had, of de titel had wat origineler mogen zijn, zou ik willen zeggen. Je bent daarna een periode, ik denk een half jaar, 3/4 jaar, als, dat heette dan junior onderzoeker in dienst genomen. Dat was omdat we van overtuigd waren, we gaan iets met softrobotica doen. Het enige, een klein probleempje was dat er was wat funding nodig om je te betalen. En we waren in afwachting van het Wearable Robotics perspectiefprogramma dat zou worden goedgekeurd en zou kunnen starten. Dus vandaar eerst die periode als junior onderzoeker. Als ik me goed herinner was het de bedoeling om een artikel te maken van je afstudeerwerk. Volgens mij is dat artikel eigenlijk niet echt geworden wat het is, maar het is een ander soort, een beetje anders geworden, maar goed, dat is verder ook niet zo erg. Je had ervoor gekozen om als promovendus voor 5 jaar aan de slag te gaan, want je voelde natuurlijk al van, ik heb wel wat tijd nodig om dit goed te doen, maar er was ook een regeling van, als het ware 4 jaar plus 1, maar dat je dus ook 1 dag, als het ware per week, besteedt aan onderwijsactiviteiten. En ik kan je verzekeren, ik heb het opgezocht, dat was echt, bij je onderwijs heb je ongeveer assistentie gegeven bij elk vak dat vanuit dynamica en regelen verzorgd werd. En misschien nog wel meer ook. Dynamica en regelen van robots, dynamica en regelen van mechanische systemen, modern robotics, haptics, non-linear dynamics en dan nog wat verdere dingen. Ook artwork voor slides enzovoort. Dus wat dat betreft al een hele klus op zich. Dat gezegd hebbend, in 2018 begon dus het perspectiefprogramma Wearable Robotics en wij deden daar precies onze soft robotics ding als enige binnen dat programma, maar we proberen ook, vooral en dank aan Gijs, ook toch wel na te denken van kunnen we de verbinding maken met name de sensorkant. We hebben daar pre-corona, post-corona een aantal keren over gesproken, maar misschien heeft corona ons daar een beetje genekt ook van dat is uiteindelijk de goede bedoelingen waren er en ik denk dat ze er nog steeds zijn, maar het is jammer, er zijn wat vragen over geweest. Het zou nog steeds mooi zijn om dat geïntegreerd in de softrobot op orde te krijgen. Voor mij was het een droom, moet ik zeggen. Softrobotica, ik denk dat 10 jaar geleden dat ik er zelf mee in aanraking kwam, laat ik het zo zeggen. Ik denk overigens dat er een link naar softmaterialen is. Als je je afvraagt waar komt die naamgeving vandaan, dan zijn er toch wat mensen ook in die materialenkant die worden gebruikt hebben. Maar dat was even de discussie hiervoor. Maar goed, het is natuurlijk toch een hele spannend onderwerp in actief regelen van dat soort materialen. En daar in dan de verbinding naar de robotica te maken. Dat is waar we het over hadden en waar we op dat moment in onze groep nog geen enkele ervaring in hadden. En eigenlijk pas ook daarna, ook in Nederland, de 4TU, het Soft Robotics programma, is mede toch een beetje onder dat soort impulsen ontstaan. Daar ben ik heel blij mee en daar heb jij een belangrijke rol in gespeeld. En ja, het gaat dan over het maken, het ontwerpen maken van softrobots, modelleren, regelen. En ja, dat laat je gewoon zien in jouw boekje. Nou ja, sorry, het is geen boekje, dat is een beetje het enige handicap. Het is natuurlijk een beetje dik geworden. Dat zou best minder kunnen. Tegelijkertijd een prachtig historische inleiding of samenvatting, wat ik zeer waardeer. Flink aantal artikelen, conferentiepapers. Ik heb, voordat ik naar jou als persoon ga, wil ik toch 1 ding nog in herinnering roepen. En dat staat niet in je boekje. En als je nou jezelf een beetje wil verkopen, je hebt toch ooit een prijs gehad? Die posterprijs, en ik dacht dat het $500 was. Ja, nee, maar het was $500. Dan schrijf je dat wel in je cv. Dat was voor een poster op een van de soft robotica conferenties. Dus hartstikke mooi. Eerste prijs enzovoort. Dus Brandon komt terug en hij vertelt het aan mij, waarschijnlijk ook aan Sascha. En ik heb de mail daarover nog, dus ik kan het je straks ook laten zien. Daar kun je wel een mooi flesje bier voor kopen. Dus ik heb Een paar weken later kwam Brandon uit Limburg een keer aangereisd met een prachtig flesje bier. Ik heb het opgedronken, ik weet niet meer wat voor bier, maar misschien moeten we het dan nog eens over doen. $500. Als persoon, een paar karakterisaties. Je bent volgens Sascha, maar ik weet het niet helemaal zeker, maar dan neem ik toch wat afstand. Toen je jong was, was je bedreven in karate. Klopt dat? Ja, dus, ja, oké. Enthousiast, bedreven, vriendelijk, heel zelfstandig. Haast bij het ongeremde af. Die combinatie is een gevaarlijke. Dus ik heb Brandon wel eens moeten bellen van, zullen we nou toch niet eens een keer bij elkaar gaan zitten? Want ja, je had eigenlijk dan jezelf even als laten ontsporen met, ja, er waren natuurlijk zoveel richtingen. Wel heel typisch, zo nu al moest ik je even terugroepen. Je bent geïnteresseerd in hardware en software, wat ook toch wel redelijk uniek is. Je bent een Limburger, dat is ook wel vrij uniek. Stelling 10 en 11 vind ik fantastische stellingen. Iedereen gaat nu kijken wat dat zijn, maar karakteriseren jou ook als persoon. Je bent nog aan het oriënteren wat je gaat doen, volgens mij. Die eerste optie, daar ben je ondertussen achter, dat gaat het niet worden. Ja, academia versus bedrijfsleven. Nog steeds denk ik dat je beide kan. Met jouw kwaliteiten kun je beide kanten op. In ieder geval, voor nu wil ik jou feliciteren. En daarmee natuurlijk ook je familie en vrienden. Gefeliciteerd.
Dr. Caasenbrood, also congratulations on behalf of the Doctorate Board of the Eindhoven University of Technology and the Department Board of Mechanical Engineering. Really nice to get a degree with cum laude. Ladies and gentlemen, this is really special. It's only 5% get awarded cum laude. And it's not like a committee like this which decides, but there is an external committee within the university. They send out the thesis to up to 10 reviewers all over the world. And if they all say it's cum laude, then it's cum laude. So it's really special, so you can be really proud of it. We can now wear the doctor title, update your business cards, all your social profiles, and it's really great. So you could do that right away. But there are also some duties connected to it, and I need to read this to you. The scientific degree of PhD involves duties as well as rights. As a holder of this degree, you're committed to standards of scientific integrity, trustworthiness, intellectual honesty, openness, independence, and societal responsibility. These standards are described in more detail in the Netherlands Code of Conduct for Research Integrity and in the Eindhoven Code based on it. You also have duties towards society. You must be clear about the boundaries of your own expertise, and you must communicate honestly and independently about the results of your work, including potential risk associated with it. You are committed to the ethical codes for research and design involving human subjects or animals. So with these last words, I'm going to ask you to take your seat back into the audience. Ladies and gentlemen, I'm going to close the meeting in a minute. Let me explain the procedure. After I close the meeting, the beadle is going to escort the committee outside. I'm going to ask the young doctor, together with his 2 seconds, to follow us outside. And then outside, a photograph will be taken by a professional photographer. And then everybody can come and follow and congratulate the young doctor. So with this, I close the meeting.